All right, let's dive in here to a brand new unit. We're talking about electricity. Now, I'm gonna warn you, this can be a bit of a jump away from what we've been doing. We've been dropping stuff, throwing stuff, climbing stuff. Well, not climbing stuff, but a lot of carts, a lot of ramps. This is very different. We're going to be talking about very small charges, very small things we can't really see for the most part. And this shift in focus can really be shocking for some students. But I encourage you to just stick with it and try to enjoy applying some of the ideas that we've had about physics so far. Things like, energy and force are still relevant, but we're going to look at it in a new way. And so this is talking about chapter 14 in our textbook. And it is going to be an abridged version of it. We're not doing the whole chapter. We're going to then jump over to chapter 16 in a bit later. So, electricity, what is it? Perhaps you have at one point in your life, perhaps been walking on some sort of a rug and then gone over to a doorknob and then suddenly, zap, lightning. Well, not really lightning, kind of lightning. You get a bit of a shock from something. Or perhaps you have been innocently eating a Swedish fish, a delicious fish. And you would take that wrapper, and that wrapper, you rip it open, and, it just sticks to your fingers, and you can't get off. You, go with the one hand, and it just sticks to the other hand. You're like, what the heck is going on here? The thing that's going on here is an electric interaction, a static electric interaction. Some charges are moving around, and things are happening. So, let's try to get a little more descriptive. Let's say I have two balloons, like so. They're red balloons because, I don't know, red is a nice color for balloons. What I'm going to do is rub these balloons with wool, or rub them in my hair. My hair is not wool, but what's left of it is kind of going to do the same thing. What's going to happen if I do this? The balloons, both of these, one rubbed in my hair and then kind of hung on a rope, the other one rubbed in my hair then hung on a rope. If I leave these balloons alone, they are going to push apart from each other ever so slightly after being rubbed in my hair. And that's kind of weird, right? That's not the sort of behavior that we expect to see. We don't usually see balloons having strong opinions about other balloons and being like, I'd much rather not be here right now. What this is an example of an electrostatic interaction. What I'm going to claim is that by rubbing these balloons in my hair, I have transferred some electric charge to them. And with both of these balloons having the same charge, they are going to be repelled from each other. Now we're going to get the short version of this. If you'd like a little bit more, you can check your textbook. There's a big table on page, I want to say it's 492, that kind of not only runs down this whole list of findings, but walks through some experiments similar to that, where I'm taking these two balloons and charging them in the same way and trying to get at these results. And so there are 7 big results that are important for us to think about as we think about electric interaction. The first is this claim: materials rubbed against each other acquire electric charge. This is how we're saying this thing happens. If I unwrap the Swedish fish, sometimes the wrapper sticks to me. If I scuff my feet on the rug, sometimes the door zaps me. If I rub balloons in my hair, sometimes I can stick them to walls or they hate each other. This happens. We're saying this phenomenon. We can't see anything changing. We're saying they're picking up this quantity called electric charge. Now, two objects with the same type of charge repel each other. That's what's happening with our balloons. If I rub them both in my hair, they're both getting charged in the same way, and when two things have the same kind of charge, they repel. If instead I were to rub one of the balloons on, say, saran wrap or some kind of plastic, it would acquire a different type of charge, and I might be able to get them to attract each other. That's kind of what's happening with the Swedish fish wrapper. I pull it open and I wind up getting a little bit of charge on the wrapper. I lose a little bit of charge from my hand, and suddenly the hand is like, I love you, wrapper, and wrapper's like, I love you, hand. And it's very tragic because I tear them apart. I want to eat the fish, not the wrapper. That is actually an example more so of part 4 here. This idea that two objects made of different materials rubbed against each other acquire opposite charges. We'll get back to that in one more second with the hair in my balloon, but these last ones are very important, and we're going to double back to them also later on. The magnitude, the size of the force that the charged objects exert on each other, increases when the distance between the objects decreases. So the closer they are, the stronger the force. And sometimes you can, as a result of more vigorous rubbing, you can get a greater force exerted by the rubbed objects on each other. So we might think, I would argue, later on I'll do this exact thing, the more you kind of are doing this, if I rub the balloon in my hair for longer, or if I do it like kind of more aggressively, I'm piling up more charge on that balloon. And this last one is really weird, that uncharged objects are attracted to both positively and negatively charged objects, and that uncharged metal objects are attracted more strongly than non-metal objects. This bit about kind of metal and non-metal, keep this in mind. We're going to come back to it. But all of this is kind of these are the things that we observe when we deal with these things that we're calling charged objects. So let's try to tear into them a bit. This idea being, if I take this balloon and I rub it in my hair, and this is a very uncomfortable experience, perhaps, I don't know. What I'm going to claim is that this balloon has a whole bunch of charged particles inside of it. And my hair has a whole bunch of charged particles inside of it. In fact, I'm going to claim that everything has a whole bunch of charged particles inside of it. And what's happening here is that as we rub, the different kind of materials have what they call different electronegativities, a term that we're not really going to worry about. But what that means is one of these prefers electrons more than the other. So these negatively charged particles are going to jump ship. As they leave, suddenly there's an excess. Oh, hold on. I should have counted these more carefully. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Totally balanced. And then my hair. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. Totally balanced. All right. So as these jump, I wind up with some extra negative charge on my hair, and I wind up with some excess positive charge on my balloon. And this is how we're coming and charging things. This is what we're talking about here in point 4. Two objects made of different materials. My hair is not made of balloon, and my balloon is not made of hair. Both of those are horrifying things that I wish I hadn't put in my own thoughts, but that's where we're at right now. Rubbed against each other, acquire opposite charges. And they do this by charge moving from one to the other. It could be it goes the other way. I really don't remember where hair and balloon fall on the triboelectric charging table, but go with it. The big idea here is that all matter is made of charged particles. But there are two kind of big buts. The first one, most objects don't carry a net electric charge. Remember, net means an excess, just like with net force. That means most things walking around, despite having a whole bunch of charged particles, you remember I was just going back and I was counting to make sure I wasn't misrepresenting my balloon and my hair? Most things carry around have as much positive charge as negative charge. Oh, by the way, should have mentioned this maybe. Remember this whole same type of charge? We're going to call these two types positive and negative. Positive, negative. It's very judgy, but negative. There's nothing wrong with negative charge, and positive charge can sort of be annoying sometimes, but don't worry. It's actually arbitrary. If Benjamin Franklin hadn't made a terrible mistake and called the moving charge negative charge back in the day, electrons would be positive, and not positrons, that's something altogether different. Protons would be negative, and that'd be very confusing if you think about it. Positrons being positive. Anyway, point is, most objects don't carry a net electric charge. So most stuff doesn't have extra electrons. Most stuff isn't missing electrons, having excess positive charge. Most stuff has the matching number of electrons and protons throughout its structure. And the other thing to consider here is that even though everything is made up of charged parts, that material doesn't always respond to charge in the same way. And that's, going back to this magical list, where we're trying to get at here with number 7. That uncharged objects are attracted to both positively and negatively charged objects, but this difference with the metal and non-metal objects is important. You may notice that, sometimes we make things out of plastic, for example, because, it's somehow safer. You're not going to get shocked with something. If I touch a plastic doorknob, I'm not worried. If I touch a metal doorknob, I'm always afraid that it's going to come for me and just zap my hand. This is kind of breaking our materials into two major groups. We're going to call one of them conductors. Conductors allow the flow of electricity, also of heat if you're talking about thermal conductors, but we're not. And then also insulators, which are sometimes called dielectrics, things that prevent the flow of electricity. So examples of conductors, metals, are going to be the big one. Also, water, and also you and me. The characteristic of a conductor is that it has free electrons. It's not that they are cheap or that, they're just like, BOGO or something. It's that they are able to move freely. So they can rearrange very easily. This leads to this idea that a conductor, when exposed to a charged particle, you have this big global rearrangement of charges. All the charges are going to want to move around in a way to best meet the circumstances they're in. More on that in 1 second. Insulators and dielectrics, on the other hand, that's more plastics, glass, wood to some extent. These are going to have bound electrons. The electrons are not able to rearrange. They're tightly held in place. So instead of like this free big global rearrangement as I gesture with my hands that you can't see, you have instead local rearrangement. The best example I like to use here, if you've ever seen those like kid leash backpack things. You give this small child this cute animal backpack that secretly has a leash on it. In dielectrics, in insulators, the child is on the leash. Maybe they see a candy store and the child runs to the candy store, but they're on a leash, so they can't get that far. In the case where there is a conductor, the kid sees the candy store, the kid runs to the candy store, and the leash snaps. The kid just goes and face plants right onto, the windshield there, and is just drool looking at those gumdrops or something. It's very dramatic, and some concerned parent is now chasing into the candy store after a child that is very excited. And then they sanitize because we'll try not to date the screencast too much. In 5 years, when someone watches this again, they'll wonder why I made a pause there. All right. So we've got this big thing. We know like charges attract. We know opposite charges. We know like charges repel. We know opposite charges attract. That's a nice thing I like to sum up called the law of romantic comedy, and then forget it every time I say it. Opposites attract. That's the big thing. So let's see. We'll make 2 examples here of how this works. Let's say that I have a copper cup and I have a plastic cup. And next to these cups, I am bringing a nice big positive charge. I know that inside the copper cup, all of the positive charges in there, they're free to move just like the electrons. Not really, but sure, go with it. They are all going to be repelled, so there's going to be a big pileup of positive charge on the far side of this cup. All the electrons, on the other hand, are going to line up on the near side of that cup, eager to get towards that positive charge. And this big separation that's going on here, 2 extremes, this is that global rearrangement of charge I was talking about a moment ago. Global rearrangement. Just make that a little hard to read just to cover up any spelling errors. In plastic, on the other hand, we know that we still have these, positive charges and negative charges floating around, but they're tightly coupled together. So instead of them going to extremes, we're going to wind up kind of positive charges scattered throughout, negative charges scattered throughout, and what they're going to do is line up like they're doing some kind of square dance or something, with the negative side a little closer to that external positive charge, because those negative charges want to go in that direction, and those positive charges want to go away from that direction. And what we're going to call these little things are dipoles, because they got 2 poles, a positive side and a negative side. And this is this idea of a local rearrangement. And you can see all that the copper is doing, it's making a dipole, but the dipole is the size of the entire cup. In the plastic cup, you get these dipoles and they're all scattered throughout it. Now there's one more bit of this chapter to talk about. We're going to zoom in a little bit more. That's a bad joke, sorry. All right, let's say that I got 2 positive charges. I want to know how much force do these charges exert on one another. So we got to put a little bit of detail into here. We're going to have one equation in this chapter to work with. So to put some detail, I'm going to say that these 2 charges have charges Q1 and Q2. For reasons that don't make any sense, Q is our variable for charge. It is going to be measured in coulombs. And the Coulomb is going to be just a capital C. And I'm going to separate these 2 charges by some distance that I'm going to call R. R is just going to be measured like usual in meters. So, recall, we have this big table of observations, right? The two of them that we want to worry about here are these two, talking about how much force there is. The magnitude of the force that the charged objects exert on each other increases when the distance decreases, and sometimes more vigorous rubbing leads to a greater force. So, what we're saying here is more distance, less force, and more rubbing, well, that's going to get us more charge, we said, more force. We can again go take a look in the textbook, somewhere around page 502, 505, somewhere in that neighborhood, is another table kind of walking through some experiments, trying to see exactly, as we increase the distance between these things, what are we seeing in terms of motion? As we, split charges and make charges smaller, what do we see? Well, what we see is what we're going to call Coulomb's law. It is a relationship between, or it's the relationship of the electrostatic force between, it's the force between two charged objects, Q1 and Q2, separated by a distance r. So this fancy setup that we had up here, right? Two charges, Q1, Q2, distance between them, r. This is what we call an inverse square law. So, called because down here we have a squared, r squared, and it's chilling out in the bottom. So, as we look at this, if Q1 or Q2 gets bigger, if I have more charge, then the force gets bigger. Makes sense. If r, the distance between them, gets bigger, the force gets smaller. Also makes sense. And then there's this K thing. And K is weird. So let's be clear here. Q, again, the electric charge, measured in coulombs. K is weirder. K is a proportionality constant. It's related to the fundamental law of laws of the universe. There's a bit more detail that we're just kind of sweeping under the rug and being like, it's K. Okay. K depends on the units that you use. When we use SI units, K is going to have the value 9 times 10 to the 9th newtons meter squared per coulomb squared. K is just a number. It's there to get everything to kind of work out the right way. But it means that this force can get really big sometimes. So we're going to talk a little bit about scientific notation in class. And for the most part in this chapter, we're worrying about being able to employ Coulomb's law, both thinking about what does it mean, do we get a big force or a small force? And then also, like we were doing in chapter 6, thinking about exactly how much force do we get. It's not just enough for it to be bigger or smaller. We want to be able to use that equation. Then we also want to think about these kind of interactions of charges and matter, thinking about dipoles being formed in insulators, and thinking about this big global rearrangement of charge with conductors. So really focusing on the idea of, this kid on the little leash backpack thing. So you get the local rearrangement where the kid runs around and is near the nucleus so the charges never get too far apart. Or is it this big global rearrangement where the kid just gets to run up and, smush his face on the wall of the candy store? So, yep, that's a starter for electricity. We will do more in class, including electrocuting people. It will be fun. I will see you then.